Welcome to solverfy.
Okay, for this problem, we have a laser with a wavelength of 193 nanometers. It's a pulsed laser, which delivers 1.5 times 10 to the negative 3 watts of power in a duration of 12 nanoseconds. We're first asked what type of light this is, which will depend on its wavelength only. We're then going to be asked what's the energy per photon, and lastly, how many photons are emitted in a particular pulse. So the equations we'll first need for the energy to relate it to its wavelength. The energy is related to wavelength by hc over lambda. We also need to know that the total energy in a pulse is simply the power times the duration of the pulse, because power is in joules per seconds. Multiply by seconds, you get joules. So thus, the total number of photons will be simply the total total energy of a pulse divided by the energy per photon. So let's jump into it. So first of all, we can quickly answer what type of light this is. Since the visible spectrum begins at about 300 nanometers and up, and this is considerably less than that, we can definitely say that this type of light is ultraviolet. It's not quite X-rays or gamma rays. This is ultraviolet light. So that's very, very straightforward. Now to find the energy per photon, we can simply divide hc by the wavelength we were given. We'll probably want the result in electron volts. So after multiplying through, we have 1.03 times 10 to the negative 18 joules, which we can divide by 1.6 times 10 to the negative 19 joules per eV to get our result in electron volts, which gives us a nice 6.437 electron volts. It's a good answer. Okay, so now we can find the total energy of a pulse by just multiplying the power by the delta T. And we actually combine everything into one step if we want. Might be a little bit more straightforward. The total number of photons emitted will simply be the energy of the pulse divided by the energy per photon. The energy of the pulse is simply P delta T. Energy of the photon is known quantity. So let's now get some numbers. 1.5 milliwatts times our time, which is 12 nanoseconds, divided by the energy of a particular photon, which will actually use the joule amount here, because we can't use EVs without a conversion. We're left with a result of 1.7 times 10 to the 7 photons. And you can confirm for yourself that these units will work out. We have joules per second times second. Joules divided by joules gives us no SI units. It's just units of photons. And that's it. All of the results we need. Thank you very much.